Hi everyone, I'm Justin from TSG. I'm here to talk about our structure fabricator. Uses a selective laser melting of regolith. Regolith, we're talking about soil, dirt, moon dust, or just dirt laying on the ground here at Earth. So essentially, we're building a giant laser 3D printer that uses dirt instead of metal or plastic powder. That means we can build up protective structures made out of solid rock using the dirt we have in front of us. Why are we doing this? Why are we motivated to do this? Basically, we want to enable spacefaring human civilization. We're mad that 2001: A Space Odyssey didn't happen in 2001. What's the main problem? Why isn't this hotel and this conference on the moon right now? Radiation will kill you, and the leading technologies to protect you from radiation are very, very expensive. Even those that use ISRU, the same dirt kind of things we're thinking about, gluing or melting them together, still cost a whole lot. So the solution, we want to improve on those. We want lower mass. We want it to be more effective than the NASA and ESA methods, which are the leading competitors now. And if we do that with infrared lasers, it provides a viable method that we can use right now. What's great is if you apply this to Earth, terrestrial application, you can break into the construction industry and get a lot of near-term profit. So about the technology, it's solid state, uses renewable power source. It's all automated. It's a giant robot with a giant laser. You can always solve problems like that. And you set it and forget it. It's autonomous. All these are proven technologies that we can put together in our garage right now. It just so happens that the arrangement we use, we hold the IP and it's protected. So the limitations with the competitors, NASA's using microwaves, high power consumption, low density product. They make little moon bricks. Regolith FDM with ESA, they actually have to bring binder with them. So they're taking glue to the moon to glue dirt together. Cost goes up with mass, so that's not very effective either. If you talk about the terrestrial application, the only thing that's a close analog is if we go head-to-head with heavy machinery in the construction industry. So because we don't really have any labor, material, or operations costs for our machine, 10 years of us costs $500K. 10 years of a Caterpillar bulldozer, we're talking about $3 million. So we've done some case studies. This is a simple one. This is a roadway. You can really build anything, but this is flat and simple. Order of magnitude cost reduction, all right? Nobody's using this in the construction industry, so it's like there's no similar competition, and they're burning $500 billion a year. If we can get a tiny bit of that market, it's a windfall. A little bit of risk here, yeah, because the construction industry isn't going to know about this technology, okay? They're going to think it's slow, like a 3D printer on your desktop. So what do? Technology demonstrators and trade shows. Our business model is pretty simple. We're taking it from the lab into production. In about 2 years, we can be making quite a bit. And the idea is essentially we've already seeded. We're seeking 1.15 million of Series A. That's going to give us a year of operation. What that's going to allow us to do is get that development up into the manufacturing phase, and then that'll give us time to get our advisors and contacts networked into the construction industry, because the best way to go in construction is face-to-face or business-to-business. This is our team. I have 10 years, 3 startups behind me. The rest are a little young, so we've got quite a bit of partners and advisors that are helping us along the way. After 3 years, we're looking at 1,500% ROI, and then it goes exponential from there. So you spend a little, you make a lot. Thanks for your time.
Do you guys actually have a working engineering model in the lab? And have you done, you talked about creating a roadway and bricks and things. Have you done some of these tests?
Yeah, a lot of these have actually been, people have been fooling around with this technology for a couple of years. They just haven't used the right wavelengths and used the right lasers. We have a laser in the lab right now that we do small scale testing with. We really think this is one of those ideas where people will, when they see it, they'll hit themselves in the forehead and say, oh my gosh, I should have patented that, it's so obvious. We think it's the obvious solution. Us and other labs are replicating it right now.
And then how physically big is it in terms of mass? If this does have to go into space or get launched, is it Is it,
Well,
hundreds of kilograms or?
if we're going to the lunar surface or we're going to Mars, you want to keep it curiosity size, so something small that could actually rove over the layers and make the shapes. If you're doing this on Earth, you might as well make it as large as a house. That simplifies it, and then you just have a CNC gantry that operates the laser.
It sounds like initially in the first few years you'll be doing a lot of terrestrial work, so your customers will be here on Earth and in the construction industry. How do you see that transitioning to more space applications over time? So I guess I'm asking for, if your ratio is 90% ground or Earth and 10% space now, what's that ratio going to be in 5 years and in 10 years?
Well, the idea, of course, originally was to provide radiation protection. This was a space technology, and we found that it scaled and made more money terrestrially. So over the first couple years of revenue coming in, we really want to funnel that back to the R&D on the space side. So we can use what we make here on Earth to fund ventures that are going to the moon or Mars. I'd like to see it 50-50 in 10 years maybe, but it really depends on what some of those big clients like government agencies and SpaceX, those kind, when their time frames line up.
And just following that question, so on terrestrial applications, have you gotten traction with construction companies or anything on Earth now that have looked at the product, or you haven't quite gone public yet?
Well, one of the people on our board of advisors is the local ASCE president, so he's got a lot of connections in construction. And the most I've been advised to say at this point is that there's a lot of interest, okay? We do want to bring them into the lab and show them. They want to see it happen. And if so, obviously, when you look at an order of magnitude difference, it's, something they're very interested in.
Is there a strong correlation between the radiation type products and the regolith laser type product? Is there a sharing of IP?
Oh, for the methods, sort of, because you're applying, a large amount of thermal transfer to get something to sinter or melt. All right. So the idea is that the laser is a little more efficient. You use an IR laser in the, close IR range. You're right in the middle of your black body curve. You cook it a lot faster, basically. So instead of microwaving bricks, you can make a continuous structure much quicker.